Are we live? Recording in progress. Okay. Okay. Good to go? Okay, so welcome to Data Science Retreat Demo Day for Batch 28. So if you are watching this on the streaming channels, thank you for your attention in advance. You're in for a very nice 2.5 hours. You're going to see what is possible to build today within 3 months with proper guidance. And in my opinion, I'm pretty sure you will share this, it's pretty impressive. What we humans can build right now with the technology that we have, it makes magic look kind of tame. So because of pre-trained models, because of data sets that are public and open source libraries, you can build things that feel too good to be true. So if I will tell somebody from 10 years ago that we're building the things that we are building here right now, they will laugh, they will not take it seriously. So my message to people who are checking this channel to see what is possible in machine learning, my message for you guys is that it's ridiculously cool to be in machine learning, and you are missing out if you're not. For those of you who know Data Science Retreat, this is probably old news. So we are the longest running and most advanced company training data scientists in Europe. We have the deepest curriculum in Europe and probably in the world. And we've trained people for 7 years now who have gone to some leadership positions in industry, and we're very proud of that. What you're going to see now is the presentations from teams from Batch 28. This is a group of 12 people, 9 of them had PhDs. This is actually not that important in fact, but you're going to see a level of creativity with technology that it's kind of very pleasant to see, right? So if you come here, if you are watching this stream because you are considering joining DSR in the future, look at this and start thinking already what you can build, because there's a lot of problems right now that you can solve with machine learning, and we are not solving them just because people don't know that this is possible. So it's like low-hanging fruit all over the place, and you could potentially, in your underpants, in your kitchen table with a laptop, solve problems that are affecting your life with the technology that you have in your hands right now. So let's this be an example for what you're going to experience if you come here, right? Now, if you are running a company and you are wondering if you could do better with more data scientists, and you are thinking about hiring, and the market is, from what I understand, red hot right now, look at the people who are presenting here. Watch their videos once they're published in the YouTube channel. We normally post-process them and publish them, and track them, because I'm sure these people are going to go places, and it's a good time for you to catch them before they take off. So this is the Science Retreat Batch 28. And now, without more complications, I'm going to introduce you every team. So the first team is going to work on detecting the solar panel capability of Berlin. So let me introduce you to Daniel, Jeremy, and Corsian, who is actually not here. So it's a team of 3 people. Only 2 of them are here today. Corsian is in the US, unfortunately. So Daniel and Jeremy.
Thank you, Jose. Let's just make sure we're properly set up here. Close this. Share the screen. Sorry, 1 sec. We just need to do the final setup here. the screen. Thanks. Okay, hi. Thanks for joining us today. My name's Daniel. This is Jeremy. We'll be presenting the first project here today. Kostyan unfortunately can't be with us today. He is online, but he can't present. I'm sure he's keeping an eye on us and making sure we don't say anything stupid. So our topic today is calculating the solar potential of rooftops in cities. At this point, I'd just like to say thank you to our mentor, Adam Green, who supported us throughout this project, and also to Tristan and Marcus for their help and comments on the project as we went through it. Let me just grab this. So what are we talking about here? As you may know, or maybe you don't know, some cities in the world produce solar energy potential maps. So what is that? That's basically a top-down view of a city, usually overlaid on an aerial map, and it shows for every building in that city, for every roof, how suitable it would be to install solar panels there. So if you install solar panels there, how much energy could they produce? Is it suitable or not suitable? And this is done by cities in order to make decisions in which areas maybe this sort of investment should be prioritized, but it's also useful information for homeowners or building owners to decide, is it economically feasible to install solar panels? It's basically a first view on that before going into more detailed analysis. So that's a solved problem, right? That's already done today. But there is a problem with that. The way that's normally done is using 3D data, normally LiDAR data, and combining that with other urban planning information. And that works fine. The way they do it is they build 3D models from that, then they calculate where the roofs are, they calculate the angles of the roofs, the size of the roof. And based on that, they produce these maps. And the problem with that is really just quite clear. You have to collect the LiDAR data, and that's quite expensive, and it's not available for most cities in the world. So this can only be done where you have that data available. So our question was, well, can a deep learning model, or more specifically a computer vision model, do this more easily? And what would this model have to do? It would take a visual representation, so in this case, aerial photographs, and would try from that visual information in that image to identify where the buildings are, where the roofs are, and then try to classify those roofs, again, just on the visual information in that image, how suitable they would be for solar. And then that could be used in a further step to estimate the solar potential of a particular building, or the solar potential of an entire city even. So we have some good news. The city of Berlin is very, very generous with their open data. We're very thankful for that. They produce aerial images almost every year, and they still have theirs up from 2013. And they have also, in 2013, produced a solar potential map based on the LiDAR process that I described. So they went through this effort, and we extracted this data and converted this data and combined this data. And by equal use of Python code and cursing quite a lot, we managed to get out what you see here, which is basically labeled data for a computer vision model. This represents, if you look on the right side, the 4 categories that the city of Berlin has defined. Background is black, so that's not a category, that's no roof, right? And the other categories are here in grayscale with lighter colors indicating more suitability for solar. So the white patches are very, very suitable for solar installations. So that's great. That's how we can feed it into a model. You'll see later in the presentation, we use colors just because it looks nicer, but models like these black and white, well, these grayscale images. So brilliant, right? But, well, hang on. Look in the top left corner of the image. The mask indicates there's a building, but if you look really closely, there's actually no building there. And a lot of the data looks like this. I mean, you can clearly see there are buildings there with roofs that may be suitable, but there are no labels. Maybe there were no data available for that region. There are also construction sites. If you've been to Berlin, you know there are a lot of construction sites, and often the labels still have the building that used to be there or the building that was later constructed, but the model just sees a construction site. There's also just mismatches, things that are not updated. There's no building here in the bottom right corner. It's probably demolished at some time. It looks, I mean, grass has grown there. It's been a long time ago, but the map is just not up to date in some areas. And there's also just wrong labels in there. For some reason, this railroad track is labeled as a building. That's very suitable for solar. A lot of railroad tracks are labeled that way. We're not really sure why, but it's a problem, right? So, okay, that's bad, but actually it gets worse. Most of the map is empty as far as, you know, a computer vision model is concerned. Basically, after we extracted the data, we had 100,000 tiles. Almost half, 45% of those contain no buildings. The forests or lakes or, you know, parks, there's just no building there, okay? And another 40%, so that's 85% in total. Another 40% have just a few roofs, just less than 20% of the area covered by roofs. So that means, as you see here on this image, almost 92% of the map contain no roofs, contain no usable data for the model. And what's not quite as clear from this picture, but what is equally important, among the remaining classes, so the true classes, very suitable. The highest class is 4 times as frequent as the next frequent class. So it's even the subsets of the classes themselves are unbalanced. And as you'll see, that really is a difficult problem. But I'll stop being negative and focusing on where the data is bad. We did actually manage to train models with this. We got some decent results that we think are actually useful. And Jeremy's gonna take us through how we did that and where we ended up.
Many thanks. Many thanks, Daniel. So yes, indeed. So despite all the bad news that Daniel has announced, we are still able to do something. So more specifically, what we are the best at so far is that if you look at a part of a city, we can calculate with quite a reasonable accuracy the available surface for the best installation of solar panels. And this is quite satisfactory. So if you're a city, and we can at least tell you where to focus your effort in a city. And all you need to provide us with is aerial photographies of your city. So let's talk about the machine learning models that we have been using. So we have the first type is a pixel classifier. So we have 2 classes of models. The first type is a pixel classifier. And so it's a unit with a pre-trained backbone in the unit. The first type of pixel classifier is a roof classifier, which means that on a picture, the model tells us, does it belong to a roof? Does it not belong to a roof? Second type is a multi-class pixel classifier. The model tells us whether it belongs to a roof, and if it belongs to a roof, to which kind of roof category it belongs. And of course, as you can expect with such models, it produces images which are quite pixelized. And you can see this in the upper image, the blue and yellow ones. And this is the kind of output we have to live with if you work with this type of model. The other type of model that we are using is an object detector and a classifier, namely a Mascar CNN from the Detectron 2, and other colleagues have used that model as well. So what this model produces is bounding boxes, and on roofs that we are detecting, and on the roofs, we are also producing an overlay, a masks, which tells us the exact location of the roof. The bounding boxes provide us with a roof category. Okay. As I said, the first thing that we've done is a roof classifier. And how does it look like? So we take a picture, which is the one on the right. In the middle, you have the true masks. And to the left, we have the prediction. And as you can see, it's not that bad. And if actually on a clean data set, and as you have heard, this is an issue, we actually have quite good metrics. So I will not go into details in the metric, but accuracy is, of course, means nothing in that context, considering that we have a lot of emptiness. But the ROU, the intersection of a union, which measures how good a predicting mask fits on an actual mask, it's 60%. It's not that, it's actually quite very reasonable. And to the point where we decided to use that roof classifier to pre-sort and pre-clean the 100 tiles that we had. So we looked at the worst losses on the prediction of the roof classifier on these 100 tiles as the detector for bad masks. And it worked actually quite well. And let me tell you why we've done that. If you want to clean 5,000 pictures, it takes a day, right? And we have 100,000 to clean. So this was a good step in that direction. Let's talk now about the multi-class pixel classifier. As I've told you, what we are good at so far is predicting the surface area for the best of a roof available of the best quality. And here, the best quality is a very suitable roof from the German classification. So for that model, we are predicting 4.456% on surface of area and on a test set in Berlin. And the actual value is 4.9 in that area. So this is very reasonable. For the other area, if you think at the type of data we have, they are minority categories within the roofs categories. So it's not surprising that we are worse, if not frankly worse, on the bad categories, the not suitable roofs. We are actually producing some, but it's so low what we're producing that it's not visible on the graph. So this is for the multi-class pixel classifier. And if we look at the mask RCNN, so the object detector, here we are predicting for the best category 4.94 of very suitable roof in terms of surface area, while the true value is 4.9. And this is like very satisfactory as a result. But for all other categories, it's simply not good, right? This is clear. Let's talk a little bit about metrics, or more specifically, let's not talk about metrics. If you want to go into details of the metric, I'm happy to do that, and I will be very happy to do that with someone specialized in computer visions, but they are just bad, right? And I can talk about at length why and where we are failing, but this is not the topic here. Just believe me when I'm telling you that it's not as satisfactory as the roof classifier before. Let's have a look at prediction, which are more exciting. Prediction, so these are predictions for the multi-class pixel classifier. And as you can see, in terms of roof prediction, this is quite good, right? If you look at the first line of prediction, like you recognize the roof shapes, there's no debate there. But on the first line, you see a lot of orange while the roof is supposed to be yellow, right? The best category, we are predicting the lowest, lower category. So it's not great. If you look at the second line of prediction, all the pictures are essentially of the second best category, the pink one. And what the model does actually is categorize the buildings per orientation. So if you have an orientation north-south, it is predicting a second best category, while if you have an orientation of the building south, east-west, it's predicting the best category. Let's have a look at that picture, the first row as well for the multi-class pixel classifier. The building in pink is second best category. And if you look at the prediction, it predicts the best category, and except on the left side, the second best category. And if you look at what it corresponds to on the original picture, it corresponds to a roof which is very, very steep and shadowy. So again, the model is providing us, between brackets, more information than expected. Whether it's an artifact of bad data or whatever, we cannot say. A bad prediction here, roads, train tracks are bad. So there's nothing we can do about that. We get a lot of false positive. Let's have a look at some prediction for the mask R. For the mask R, as I've mentioned before, the lowest category, meaning the not yellow, are often not well predicted. If you look at the arch on the left picture, the bottom part of the arch is lowest category and not predicted well. The same thing on the second picture. The buildings in purple are simply not seen by the model at all. And let's talk about one last problem, typical to Germany to some extent, the allotments, the Schrebergarten. The Schrebergarten are either badly labeled, like in the second line, or in a lower roof category, so rarely seen. So the predictions are bad. For those, there's nothing we can do. We get bad predictions. Okay, what are the limitations there? The model has learned from its labeled data, right? This is a problem. Like we've cleaned as much as we can, but there's an upper limit to the amount of cleaning we are willing to do. Let's be honest about that. The second thing is that the model has learned only from aerial photography, and we would like to have some more flexibility there. And also the model knows only the roofs in Berlin. If you look in Leibniz, Austria, and look at a prediction on a satellite photography in Leibniz, Austria, it's not that great. And we would like our model to be able to learn about roofs there. What needs to be done? Data cleaning, data cleaning, data cleaning, data cleaning. This is the thing to do to improve the model. We've done this several times, and each time we've done that, we've noticed significant improvements. The other problem, as you have seen, the prediction for the lower classes are bad. So dealing with class imbalance, whether for the lower classes or for the roof, no roof, is a major issue here once we have clean data. Maybe a better model is necessary. So of course, Tristan will be happy if we talk about transformer, and I'm sure he's commenting about that in the chat right now. And maybe also working with a model pre-trained on aerial photography might be a good thing, and such models exist. And meanwhile, we would really like to end up being able to produce in Jakarta a proper mask for that and make prediction in Jakarta. But for the moment, we're not there yet. As you can see, the predicting masks is not that great. Many thanks for your attention. Many thanks for the work with Daniel and Korstian, and many thanks, Korstian. If you have questions. Yes.
So we have a little bit of a complicated setup for questions. I'm going to read the chat. You're not going to see me. If you have any questions, I can read them out loud so that the presenters can see them. Okay, so one question is, are the pictures oriented by north, south, west, and east? Okay, so it's yes, very fast.
So let me give a longer yes to that. Obviously, we tried a lot of data augmentation, rotating. I mean, so the images you've seen are all north oriented, and that's important because the north-south orientation of a roof is very important in its category. We did try quite a lot of data augmentation. This helps particularly on detecting roof or no roof. So there you can rotate, you can resize, you can squeeze, you can work with the brightness and all of this. But that's slightly more dangerous to do with the actual category detection, because all these factors, and especially the north-south, east-west orientation, is really important for the category. So it would be dangerous to augment in that way, that you rotate the images or flip the images.
So that takes out a big part of data augmentation, which is rotation of images. You cannot do it because the sun is important.
It does, and we have considered whether it would be worthwhile to split it into two models, one that detects the roofs where you can do heavy augmentation, and one which does the categorization where you have to be more careful with the augmentation. But that's sort of on the to-do list as well.
Okay, so this is a clarification question. You have data only for Berlin, right? So if you have data for more cities, you could potentially extrapolate to the rest of Germany.
Well, we don't have only data for Berlin. We also have data for detailed data, some amount of detailed data for Potsdam, which we haven't used. There's probably also data elsewhere, but the data for Berlin were readily there to be used, right? And this was a low-hanging fruit in terms of availability of data.
Just in general, I think the models are generalizable to other cities, but the data would have to be annotated in the same way. There's some complication about that. Cities produce these maps, but they often define slightly different categories or slightly different ways that they label the roofs. So there is complication about that, but in general, the models would be viable for other cities. And that's definitely what we wanted to do. As Jeremy is saying, Jakarta, Mexico City, we wanted to work there. So what we need is more and cleaner data for that.
Camera as well. So, but the whole point here is that you could potentially, if you do the generalization of all of Germany, let's say that you had data at some point that allows you to generalize to all of Germany, you could calculate the capacity, the solar absorption capacity of Germany, right?
Correct, and that's actually why we're. Oh, sorry, I'm not actually in here. Why we're quite happy with the fact that it's predicted, and why we focused on the area of the highest solar category, because the area will actually give you a good indicator and allow you to start making calculations. A certain part of a city, if you have a certain area of roof of that highest category, how much solar could you produce there, and that'll allow you to make these calculations even based on the estimates we already have for Berlin.
Sounds very interesting. I'm sure some politicians may want to hear more about this at some point. Okay, so second round of applause. Right, so our next team is trying to find all ping pong tables in the world. So this is one of the things that I mentioned when I say that you can solve your own problems with machine learning, right? So if you like ping pong, you don't know where to find the closest table. This team decided they wanted to do something about it, and they did. And it works not only for Berlin, but for the entire world, right?
Yes, that's the idea, that it will do that.
Okay, so Sabine and George.
Okay, so welcome everyone, good evening. My name is Sabine Reister.
And I'm Georgios Mikhail.
And we both like ping pong. So, and we like to play ping pong everywhere. We like to play ping pong on our holidays. We like to play ping pong at home. We like to play ping pong on the playground, wherever. And also like in Spain, in Cyprus, in Greece, wherever, in Jakarta, everywhere we want to play ping pong and we want to find ping pong tables. And this is why we created Anna's Ping Pong. So you will meet Anna later, just if you're wondering why it's called Anna's Ping Pong. And so Anna's Ping Pong is a web application which has a Google Maps interface and which enables you to find ping pong tables at any location where you are. And now George will guide you through our approach.
Thank you, Sabine. So to create this application, to solve this problem, we used the following strategy. So we first created the data set, which consisted of aerial images, similar to what the previous group has used. And then these aerial images, or so-called map tiles, contain ping pong tables. And we had a lot of them. And then once we created our data set, then we used this data to train an object detection model, which ideally, when you provide it with an input image, an input map tile, it would just tell you whether there's a ping pong table on it and where exactly. And then on the last step, we employed this, we used this trained model to create an application where you could just go to an area you like, for example, in Google Maps, and then you click a button and then you get a prediction whether there is a table in this area and where exactly that is. And now Sabine is going to explain how we created the data set.
Yes, so of course you can imagine that there are a few challenges. So these map tiles that George mentioned, have a side length of about 20 meters and a ping pong table is about 2 meters long. So for a map tile, they are actually comparably small objects. At the same time, we have problems that in these aerial images, often they're taken in the summer and there's a lot of shades and there are also a lot of trees that are covering the table, so they're not always clearly visible, as you can see in the middle image. And then on the right, you see that some of the map tiles actually have varying resolutions. So the one on top has a good resolution, but the one below is just half of the resolution. So these are different problems that that we're facing here. For the generation of the training set, we were lucky that someone else had actually already the same idea. They just had a completely different approach. So on pingpongmap.net, you find an application which you see on the right, which is also a map, and you have positions of ping pong tables on there. The difference is that in this case, this data set was created by a large community of ping pong players that actually went physically to the tables and used their phones to tag these tables. So they saved the GPS coordinates and tag these tables on the map, and so they were saved in the data set. And this is how we got our reference data set. So luckily, we didn't have to browse through all of Berlin and collect all of these GPS coordinates ourselves. So what we did to generate our training data set was then to download map tiles from Bing Maps. And then we used also some data augmentation by shifting the tiles that I will explain in detail. And then we labeled the tables on the tiles with bounding boxes. And this gave us in the end a training data set of roughly 1,400 tiles. So looking through all of these tables can actually be quite inspiring because it really makes you want to go out and play. Like, for example, this one on the left side where we have the swimming pool, and then you see on the, like, a little bit on the right side, there is this, in the center, there is this blue rectangle, which is the table, and well, it's a wonderful location. And also on the right, we have a table which is on the beach by a lake. So how did we select now the positive samples? So we had our reference tables list from the web page that I was mentioning. So we had latitude and longitude for all of the tables, but these were mostly approximate positions, kind of, because I mean, not on every phone, like it gives the GPS coordinates accurately to the centimeter, and maybe sometimes people were just standing a bit off of the table when they were saving the location. So we used a specific approach to get the real tile. So what we did, first, we transformed this latitude and longitude to map coordinates. And this gave us one specific tile. And you see in this case, the table is actually on there. It's on the top. You see a tiny part of the table. But of course, we would like, for training data, we would like to have the tiles which actually contain the complete table. So we shifted this tile to the top. And this already gave us the one tile with whole table. Then we shifted it also to the right, and we shifted it also to the right and to the top. And then we did this also in all other directions. So in the end, we had 9 tiles for each position that we found in the reference data set. And then from these, we just chose the ones which actually contained the table or part of the table and added them to our data set. Then we used label me to create bounding boxes. So the bounding box is just defined by 2 points, by 2 diagonal corners with X and Y coordinates. And this was our training data set, which we then used for an object detection model, which George will walk you through.
So after creating the data set, as Sabine described, and so we moved to selecting and training a model. And we chose an object detection model, which ideally would, when provided with a map tile as input, would tell us whether there is a ping pong table on it and where exactly that is. One attractive alternative was to use image classification. And this image classification would then be, so we provide the model a map tile, and then it just tells us there is a ping pong table or there is none. So it doesn't give us, it wouldn't give us the exact location. So, and we went for an object detection model for 2 reasons. The one is obvious. So with object detection, we would get the exact location of the ping pong table on the map tile. So this, we're going to have a better localization. And then the second reason is after some initial experiments we did, we realized that when dealing with this kind of problems with a small and relatively unclear target as a ping pong table, using bounding boxes when training the model, it really improves performances because then the model knows exactly where to look. So we used an object detection model. For those interested, I include some details for the model and the training on the slides. I'm not going to go into detail now. Just going to mention we used a pre-trained network from Detectron 2. And then also at the very end, I mentioned that we used average precision as the metric to evaluate how good our model was on the validation data. And I'm going to briefly explain what does this mean later. So the first step when one wants to train a model is to split the data in the training and the validation subset. And so the training is used for training the model and the validation for evaluating the performance of the model. And usually data scientists do this by randomly assigning data to training and validation, typically 80% training and 20% validation. In our case, doing this randomly had a danger. We could be in the case where map tiles belonging to one table would be assigned to both training and validation. And that's not good. And that's really not good because then this would mean that we would evaluate the performance of the model with images that are quite similar to images that the model has already seen during training. This is so-called information leakage. So to avoid that, we made sure that map tiles corresponding to one particular table were assigned either to training or to validation, but not both. This figure shows the performance of our model as evaluated by the average precision measure that I described before. Average precision is a standard metric that is used for object detection. As Jeremy explained before, talking about metrics, we could do that, but I think it's not for a 15-minute presentation. Just to give you an idea, average precision takes into account both false positives and false negatives. That means the cases where the model predicted a table when there was no table, and the cases where there was a table and the model couldn't find it. And what you see in our plot is that at the beginning, the model didn't have good average precision, but then after around 5,000 iterations, the model reached quite good average precision, and then there was a trend of increasing, but it remained more or less stable. And this level of average precision translates to quite good predictions. And I'm gonna show you some examples that are less abstract than this graph. So here you have an example of how our model, the predictions of the model at early stages versus late stages of training. As you can see in this example, there are 3 tables, and then early during training, the model would identify with high confidence the middle table, with low confidence the top one, and then it couldn't find the bottom table at all. However, after a longer training, our model was quite confidently predicting all 3 tables. So it became quite good, even when these tables are quite difficult to find, actually. So another example, at the beginning, our model tend to think that cars, especially white ones, are ping pong tables. But later on, it learned that cars are not ping pong tables. And then this is another example where it's a relatively difficult ping pong table in the middle, which is partly shaded. At the beginning, the model couldn't find that, but then at the end, it predicted it very confidently. So our model, although being quite good, it's not perfect. And here we have some examples where the model predicted a table that predicted something is a table while it's not. So in the first example, you get a bench predicted as ping pong table. And then the second one, you have some shaded objects with some lines that the model confused the model to think there's a ping pong table. And there are also some examples of false negatives, meaning examples that the model couldn't find a table. So in the first one, we would expect the model to find this one, and we're a bit surprised it didn't. It might be that it was confused by the shape of the shades. And then in the second image, there is a table that we can't complain. This is a really difficult example. So it's not surprising that the model couldn't find that one. And now, after training the model, we employed it to create an application, and Sabine is going to walk you through with a demonstration.
Thanks. Okay, so yeah, I don't need this. Thank you. So now this is the demo. This is the live application which we deployed on AWS. This is a temporary IP, so this will you unfortunately won't be able to find this anymore after the presentation. So you see here's the map, and now I'm going to hit this button here, find tables here, and we're going to predict to see if it can find a table. So what's actually happening here is so this is a normal Google Maps API, a JavaScript API. The whole application has been programmed with Flask, and and what it does is when you navigate to a certain region on the map, then it downloads tiles in an area of 100 times 100 meters in the center of the map, and then it runs the prediction on the downloaded tiles, and then which means that it predicts bounding boxes, and then it checks if there are any bounding boxes which are overlapping, and if yes, then overlapping bounding boxes are discarded, and otherwise then the center of the bounding box is then converted to GPS coordinates, so to latitude and longitude, and and then it's added to a database and hopefully it's finishing at some point. And then this is supposed to be shown on the map. So yes, and we included a GIF, so not to make this waiting time too boring. And yeah, some other things that you can do. So you can just, there we go. Okay, so now the prediction has finished, and you see actually, yes, here's a table, and there are even people playing. So it worked, and so you can use these the buttons on the left also to first to go to your current location, so to use the GPS function of the browser. You can also just search for different place and explore that area. And so the whole idea of Anna's Ping Pong is to have a web application which is where the users are part of the exploration. So together we explore the whole world and find all the ping pong tables in the world. So wherever you are, you use it, and then the ping pong tables that you find will be added to the map. And now we go back to the presentation. So we're almost at the end. Yeah, just to the outlook. So as you've seen, the model is not yet perfect, so we still have some false positive that we need to improve. So a few things that come to our mind is we could work on the training data. We would also like to predict tables based on different kinds of maps, for example, of Esri World, image, or Mapbox. Also, it would be super beneficial if we had images from different seasons, like for example, from winter, where the tables are not covered by trees. And then we could also apply this tile shifting, which we explained which we use for the training data also during the prediction. And then of course we want to publish a fully functional HTTPS web server. Yes, so thanks a lot to Lina and Tristan who supported us with the project. And thanks to the whole team of DSR, which are really doing a great job of running this whole thing. And we learned a lot, and it was a lot of fun. And of course, mostly thanks to all the other colleagues and students from the DSR, from the batch 28. You're the greatest, and it was a pleasure. And yeah, and so that's it. Thank you for your attention, and happy ping pong playing.
So anybody who wants to throw questions at the presenters, please do so. Now we're going to check the chat and then read the question out loud. So you've seen, sorry, yeah, okay, we have questions from the room, okay. Igor. Come. By the way, this was two projects using satellite images, which is kind of showing how important this data is right now.
Just one simple question. If a tennis table would be transported by car and it will be placed on a car, what do you expect?
Do you get the question?
Yeah,
if it's visible from a satellite image, yes.
Because it said that cars are, it knows that ping pong tables are not cars, but what if a car is on a, no, the ping pong table is on a car?
No, I think, yeah. But I think it's our model learned pretty well to distinguish cars and ping pong tables. So I think in this case, it wouldn't be confused. Yeah.
So, and what would the answer? Would it be a table or car?
We don't predict cars, we predict ping pong tables. It's kind of say one class. Yeah. It would be a problem if we had both. Yeah, you're right.
So this may be the question that is in everybody's mind. Like the military guys may be looking at this and saying, ping pong tables, what about tanks or other things, right? How easy it is to retrain the model to target any other object?
Yeah, I think it's the idea is pretty straightforward, and I'm sure there is already applications which use a bit even more advanced models than what we use.
Yeah, actually, I hope that I'm strongly assuming that military has better approach than we do. I mean, a better model.
Yes, and I'm sure even there's because yes, and there's also that you can have there's a possibility to have live, almost live satellite imagery, which then makes more sense for military applications. So there's definitely applications on this direction.
Okay, so imagine that you are a sci-fi author and you are watching this presentation. So the technology to detect an object, in this case, ping pong table, anywhere in the world is so easy to use that a team of 2 people can do it in 3 months. So imagine the potential for kind of evil minds trying to do things with this, right? So it's totally there. And they probably have more resources than we have here, right? So right now, if you look up, maybe somebody is detecting what we are doing already. Okay. So if there are no more questions, then we should go to the next thing. Check. Yes. All right. Our next team is going to try to solve a problem that you may have, which is death by PowerPoint, right? So you may go to too many meetings. You may find that some meetings you didn't need to be there. Somebody could summarize the meeting for you. Probably some people take over the meeting. These things have happened to you, right? You can relate. So let's see what you can do with machine learning to solve that problem or constellation of problems. So Lila, Sam, and Jose.
Thank you. You guys want to come until I... So hi everyone, we are the Meeting Notes AI team. It's me, Jose, and Sam, and I should have done the order wrong. Anyways, so before I kick off, I just wanted to ask you a question to you guys on YouTube as well. How many of you have been to a meeting? Okay, a couple. So how many of you have been to a bad meeting? All right, kind of the same same amount. So we kind of had the same pain, and we wanted to kind of find a solution, avoid the problem, and that's how we came to our problem statement. So team leads and executives spend an average of kind of 23 hours per week on meetings, which means it's more than 50% of their time. And mostly it's about kind of spending time on bad meetings, which you could avoid with an email as well. So unless you join in, there is no automated way to have a glimpse of like what the meeting was about, what kind of decisions were made, what kind of deadlines were agreed. And also there is no way to see if the meeting went downhill in terms of like people got upset. And also there is no way to have an idea if you could have done something better on the meeting. So there's no way to kind of reach higher efficiency. So, and plus all this is not measurable really. So we wanted to see if we can find a solution, and our objective, our objective was to optimize meeting performance by providing a meeting summary and some collaboration insights based on an AI, so using an AI-based product. So you don't have to be there to just listen in. You can just read the summary later when you need it, actually. So we built a MVP, a minimum viable product. Because we were shown on time, we wanted to use existing solutions. So we wanted to conjure something together using these. And this is like what you see is basically what we've done. This is how it works. So you basically have a recorded meeting, and then you transcribe it with speech-to-text technologies, and then you get like collaboration insights, meeting summary, and sentiment score from it. And here you can see on the slide kind of existing solutions we used. And now Jose will take you through the technical aspects of the whole.
Thank you very much, Lila. Well, as she said, we are going to cover the technical aspect of the product. First of all, we are going to talk about the product architecture. So the product is ready to use any kind of input. Doesn't matter if it's an audio, it doesn't matter if it's a video from Zoom, Teams, or even Google Meetings. It just need a meeting, a video. So here on the right, you can see a transcript of a real meeting, which we have been using for this demo. The next step is to get the text from the speech. So we were evaluating the possibility of making our own tool to get this transcript. However, we realized that there are a bunch of existing solutions which already provide a really nice result. So we test all of them, and at the end, we went for the TEMI product, which provide a really nice accuracy and also an affordable cost. So one of the most important steps in the project is the selection of the rights model. We went to the state of art for the transformers, and we realized that the Batch large model is one of the widest used around this for this summarization task. So we select a pre-trained model, pre-trained on a CNN mail dataset, which is a mailing dataset inside a company, which makes a lot of sense regarding our purpose. So now my colleague Sam is going to explain the technical aspect of the model.
Yeah, so as Jose mentioned, we use the BART model, which is a combination of the two state-of-the-art language translation model, the BERT and the GPT combined together. And it was a pre-trained model that's trained on the CNN news summary data set. And we took this pre-trained model and did some fine-tuning on it, mainly by freezing the entire model and unfreeze the very last two layers, and then train on this Samsung dataset, which is a dataset of 16,000 messages of everyday conversations and their summaries. And because the model was already very good, we didn't have to do too much training, and the training statistics looks pretty good as well. So that's the model we use. Now, to give you a summary of our pipeline, we took the text, the original transcript, because it's too big to feed into the model. We have to divide it into several chunks. So we divide it into several overlapping chunks and feed each chunk separately into the model and generate a summary for each of those chunks. Then we concatenate those chunks together to get a single summary. But this summary is still too big, so we did the process once again, feed the summary back into the model. And then we get this summary of summary, and that's what you see at the end. Now, Jose is going to talk about the sentiment analysis we did.
Thank you, Sam. For the sentiment analysis task, we have used a direct pre-trained model, which already provides us with an average sentiment analysis for the whole transcript. But how did we feed this model? We also took small chunks of the book and got a sentiment score for each of one of them. Then we averaged them, and we established a threshold. This is at 65%. If we got a negative result higher than the 55%, the meeting is going to be considered as a negative meeting. Why did we establish this threshold? Because we didn't want it to label a meeting as a negative when it is positive. So here, like, we are trying to avoid this issue. So now we are going to prepare for the demo. We use Streamlit to create a web application, and then we deploy it on AWS. To show it. So now, okay, now we are going to import the file, which is direct a transcript of the meeting. You saw a piece of it during the presentation. Okay, and now it's loading. It's going to take a while because of AWS, but then here you will see, apart from the summary of summary, which my colleague Sam have been talking about, but also from the real transcript, you want to check exactly what each participant has told. You could also check the sentiment analysis for the whole transcript and also get some insight, which could be quite useful for the management. So, as I said, it's going to take a while.
How is the instance?
Well, what do you say for the instance?
Okay. Which one?
Sure.
I think it was one of the larger AWS instances. I think it was a 4 gigabyte memory. No, it's running on CPU. I don't think we need a GPU because it's not doing training. It's just doing inference. Yeah, exactly. So this transcript is actually we talk about actual Zoom meeting and turning into transcript. So it's an actual meeting transcript. I think it was 45 minutes. I think this transcript maybe 5 or 6 people. Yeah, but we're happy to take questions like right now. We use BART because it's probably the best model we came across, and we look at the summaries. It's by far the best performing one.
Yes, we made many testing, and we got the best result using this one. Also with different data sets, but the highest result we got with this way. So now should be. It's not gonna take, yeah. So now we got this summary of. We are getting the summary of summaries. The approach I'm already explaining, and after that, sentiment analysis is going to be as a glimpse. Did we try or analyze? I mean, for fine tuning, you mean? For the fine tuning, we use just one data set, but it contains like 16,000 conversations. So fair enough. Yeah. Okay, now we are there. So here you can see an interactive dashboard. Here you got the summary of summaries, as you can see. Here you got the whole transcript we have been talking about. On the right here, you got the meeting's sentiment. So the result, the average result is a positive one. And here this is an interactive pie chart where you see each speaker, the percentage of time he has been talking, and also the number of interaction. So here a management staff could check if someone is not participating in the meetings, could check if he only participated one, if it's so small, you can get some insights. So, yeah. Mm-hmm. Okay. Yeah, here also we can see like a couple of action detection, a kind of action detection. We got a really short summary, but we got the most important thing, the meeting. If we also try to approach in a different way, we improve the overlapping fraction. Some talk about that. If we increase it, we get a longer summary and we got more information. So we are ready. So we'll come back to the slides. This one, right? I cannot see. Yeah. Right. Okay. So finally, the conclusion. Well, for the conclusion, we have a basic one. The first one, we didn't need to reinvent the wheel to add value to our organization, creating a AI-based product. The second one is it's about transfer learning. We found it so useful because we save a lot of time. We got a really nice result in a really short amount of time. And the last one, we were able to deliver some insight for organization, which will help them to assess how their meetings are going, if their culture is getting to the people also. So also, yeah, the next step for this product will be like to implement directly to create a Zoom app to work directly with Zoom. Also to improve our action detection feature. And also, if we get access to a bigger organization, we could try to analyze the social network between not only inside a meeting, but also a department, an area. That's all. So thank you very much. If you have any question.
So guys, any questions in the streaming audience or in the room? There's actually quite a few people in the room right now. Okay, so I have one. So it may not be so obvious. If you are the manager of a small company, you may not care so much about who is participating in the meetings because you know everybody, you go for lunch together. It's kind of easy to understand how people are dealing with each other, right? But it doesn't work that way in a big organization, right? Imagine an organization of thousands or potentially hundreds of thousands of people, right? Meetings are a really costly thing for the company. So imagine the cost per person in a meeting with 20 people, right? It's very costly. So Lady, could you talk more about how you decided to do this type of project? Because it's part of your background, right? This is something that you did for consulting?
Yes, so I have a consulting background, but I was kind of mainly focusing on culture and processes in companies or developing and improving them. There is definitely a thing with meetings, especially if people are spending a lot of unnecessary time on them. And there's a huge cost involved, especially, I don't know, you imagine that you're just there wasting your time, like, I don't know, 5 hours per day on meetings that you actually shouldn't be involved in. You just need to be informed, and yeah, you just need to get the kind of important decisions of that meeting. That's why I came up with this idea. But also, as a side note, there is something similar out there, which is called Otter AI, which also gives me inspiration to check out if we can do this, if we can build the same stuff with what we learned at DSR, basically.
Right. So I also know that there was plans to make a plugin for Microsoft Teams or some kind of app. They have some app system, right? Did you try to go that route and it was too complicated, or did you actually not spend any time? I wonder how difficult that will be. Maybe Sam knows more about this.
Yeah, I think that would be the next step to make something that integrate with the existing Zoom apps, and yeah, but that's still in the works.
But did you try to do the Microsoft Teams one?
Not Microsoft Teams at the moment.
We tried Zoom, but you need like a pro account and a business account to even get the recorded meeting and the transcript, and you can only get the business account if you have like 100 or like, I don't know, 20 people signed up. So you need to pay like, I don't know, like €1,000 just to test. So that was not really feasible.
And we run out of time. We have a limited amount of time, so we did what we could.
And the data was from YouTube videos, right? The public YouTube videos. Yeah. Right. Right. So I guess it's not easy for a company to say yes to this, like, oh, give me all your meetings. I'm not going to do anything evil with them, but I'm going to know everything you discussed, right? Yeah.
That's completely right. But they would be interested on maybe hire us or to use our product and to use Insight, like a tool for them to work in the Insight culture. So, yeah.
So maybe because meetings are so sensitive, sometimes they will want your code to run on their premises, something like that, right? Which adds complexity for deploying the product, right? So I don't know if I would trust anybody to watch meetings from any company that I'm involved with, you know.
But if it's an employee of you, maybe yes, right? If it's working for the company, you could let Arum or or Avin, right? So you answer.
Yeah, you know, I'm thinking more of the big guys, right? So say Volkswagen, like they will have a hard time letting anybody listen to, even machine learning, listen to their conversations internally, right?
That's right. also depends on the topic. Maybe you have a topic which is completely confidential. You cannot talk about it. You cannot expose the people on the topic, but there are others that you can assess it and you can check how the people is behaving. So it could be also useful.
Actually, most of the big companies that you talk about are already using a lot of these products, which are tracking your laptop, what you're doing on your laptop, where you're logging in, where you're logging out, all these kind of things. So it's not really a new thing, unfortunately. Or I don't know, you basically sign this with your employee agreement.
Okay, cool. So another round of applause. All right, so if you are logged into this channel, you probably know that machines can see, that machines can hear, machines can understand language, not so well, but we're getting there. How about machines that could smell? That will be interesting too, right? So this team is going to tell you more about this. And they are going to show you a hardware project that uses sensors to identify things, products, food. It's actually a very general use type of product, right? So they're going to go through different types of things that you could classify by just smelling them, but you can also use your imagination and think up of use cases for a machine that can smell. So if we are good to go, then let me introduce you. Hey, are we good? No? Okay, no. Right. So, okay, so this sensor is super cheap, right? Igor, how much do you pay for this?
Actually, the price of the sensor was like 30 euro. So, and it's already advanced one. Yeah.
And with that, you can put it anywhere, like on a phone, on a car.
You start to ask questions too early, because this is the one of the most interesting parts of our project. And yeah, right.
Okay.
We will talk about it.
Okay, and you also use, so I know that you are a hardware hacker, right? You also use a terminal thing, you call it terminal, that's kind of a tiny little screen. So this could be completely detached from a computer, right?
In general, yes. There is a really nice device called Wire Terminal. And it is basically like Arduino board, like microcontroller with a screen on it and a small joystick. Yeah, and actually you may even play some games. Yeah, exactly, right, this one. So it's possible to use this terminal afterwards, but for our project, we decided not to go so far because it will take a lot of time also to learn how to program, how to make a real nice user interface, so that it will be useful, not just like just some number.
Okay. So potentially you can give somebody a machine, a self-contained machine that has a screen, a joystick, and a nose, and for less than 100 users.
Right, exactly.
So cool. So Igor,
Hi, ladies and gentlemen. Welcome to our portfolio project. And then it's about AI sense on digital nodes. So today I'm Hazel, and this is Igor, my partner for this program. And then we're gonna share about what we did and then things like that. And then we have our mentor is Paul and also Tristan. So this is a picture of us and our sensor, which I'm holding in our hand. And then at the end, we will have a live demo. So do you guys all know that we all humans have 5 senses? We have eyesight, we have smell, nose, we have mouth to taste, hearing, and then touch. So on AI, there's a lot of project that is being done on, let's say, sound. For example, you can relate to Alexa or Echo. And then there's a lot of project doing on the site, for example, computer vision, for example, autonomous car, for example, on the text, NLP, things like that. So, and then on the touch, you may see a lot of robotics things going on the AI project. So there's not that many projects that is being done on smell. And then you may wonder, can AI smell? And the answer is yes. So we're gonna go through our project step by step. So there's 7 little section of it. And the first one is introduction, which I just made. And then we're gonna share about the possible use case, the hardware, the data collection, predictive modeling, lesson learned, and deployment. So first of all, it's a supervised learning, and then it's also a classification problem. And then, so the following tasks we have accomplished in the last 1 month, for example, data collection. We collect a lot of sample, a lot of data in different condition. For example, in room temperature, in outside where it is super cold at 2 degrees outside. And then we also put it into a, like in a bathroom where the humidity level is very high, and then check to see if the same food give out the same answer, and then you guys will see it in a minute. And then afterward, we do analysis, transformation, and then we have, at the beginning, we have collect data for 30 classes. And then later on, we decide to truncate it and then try to condense it and then focus on 13 classes to be predicted. And then later on, we have a lot of trial and error, and then we try to pick out the most suitable machine learning model. And then we train it, experiment it, and then later on it's for the final prototype. So you may ask, what is this for, right? So so AI, there's unlimited possibility. So I'm gonna share top 5 that I choose for. And then actually everything that you can think of could use this device for. So I'm just putting some of the major one. So the first one is anosmia. So it means loss of smell. Do you know that it actually affects 2% of population because they loss of smell? And then actually 2% is an understatement. If you look at COVID number, number 1 symptom of those people is loss of smell and taste. Some people lost it permanently, some people lost it temporarily for a couple months. So this device is actually born in a good timing to be able to detect the smell for the food, for something that people really want to taste and then don't know what that is and things like that. And then second is smart kitchen. Let's say if you have an oven, let's say if you have a chicken, you know that different manufacturer of oven, it may take like 40 minutes for a chicken to be done. And then it could also take 1 hour and 10 minutes. So instead of like keep going to the oven back and forth and then checking whether your chicken is ready or not, if you have a sensor that is built into your kitchen device, then it will tell whether the chicken is cooked or not, and then turn off the oven automatically by itself, for example. And then the next one is health check. So let's say if you have a watch with a gas sensor that is built in, and then every morning when you woke up, you kind of blow your breath in it, and then the indication can show you whether your diabetes level is low, high, and then or whether your oxygen level is good or not. So it's a pre-detection of any like serious disease that could be coming up in the future. And then the next one is my favorite one. So the next one is best coffee. Let's say if you go to Starbucks and then you order a coffee, and then you know that like different barista, if someone is a student and then working for Starbucks in the first day compared to someone who is working for Starbucks for 10 years already, the quality of the same cup of cappuccino could highly vary. So instead of hopefully you get a really experienced barista from Starbucks, if you have this machine that can control the quality of the coffee, that will make a huge difference. And then that will also give customer a promising result of, okay, I'm sure that I'll get the best coffee, the best cappuccino, stuff like that. Last but not least, if you have one of these sensors in your fridge, and then have you ever have chance that you bought some milk or egg into your fridge, and then later you find out that it's been bad after you drank it, and then you have stomach ache. So this will help you, save you some time going to toilet. And then, yeah.
Thank you, Hazel. Coming to the hardware part, how we have realized this project. Obviously, for this, we took different pieces of different hardware, and first and the most main piece is visible on the top left image is the gas sensor itself. If you wonder how big it is just like this size. So compared to the microphone, it's just really small. We also used for the measurements on the bottom right image is a temperature and humidity sensor, so that the measurements are combined. For the reading, we used two options, wire terminal and Arduino Uno, which helped us to just read the data from the sensor into computer. So coming to the question how the sensor is working, what it is basically reading. You may have seen there are like 4 parts, like 4 small squares. And basically these are the 4 heads of the sensor, and means that this is the multi-channel sensor, and it measures 4 different types of gases. It is carbon monoxide, nitrogen dioxide, alcohol, C2H5OH, and volatile organic components. Also, the second sensor is also reading the temperature and humidity for recording the environment. And to this point, we will come a little later. For the data acquisition with these sensors, we basically took different pieces of objects, mainly food, only food. You may see on the images, especially on the right bottom images. So we put the samples into a glass and cover it with the piece of paper. And it's also here, and we will show it later. We will show it also later at the live demo, how it looks like. And yeah, basically we just let the sensor smell something.
All right. So throughout the project, we try to have a balanced data. So we try to have the same amount of sample of each classes after we decide to have 13 classes. So we try to keep the same amount of sample. That's why you can see on the pie chart that every category of food have almost equal share of percentage overall. And then this is one of the things that I mentioned earlier. So for example, coffee, you see 3 charts are here. So they are being detected on 3 different conditions. So the one on the right-hand side is the room temperature, which is about 25 degrees. And the one in the middle is outside. For now in Berlin, it's around like 2 degrees outside. And then the next one is a very humid room. For example, a room with that had just taken a shower, or a room with a humidifier. So as you can see on the x-axis is the time, and then on the y-axis is the value of those 4 elements. And then you can see that they are similar in some way, and they are also different in some way. That actually the graph change some of the factor has been changed according to different temperature and humidity. Okay, so you look at the presentation and you wonder what are all these numbers about: 6, 13, 120, 10, 1,200, 15,600, 98%. So those are our secret sauce for the project. And I'm gonna share one by one with you. So 6, we have 6 features. As described by Igor earlier, we have 4 elements that is predictive detected from the sensor, which is the CO, NO2, alcohol, and the volatile compounds. And the last 2 elements is the temperature and humidity. 13. So we have 13 classes of food, and then 1/22. So the measurement is 1/22 for each of the sample. And then 10 is the hertz. It measures how often per second data is read. And the next one is 120 times 10 is 1,200. So we have 1,200 observation per classes. And the 15,600 is the total observation. So 1,200 times 13 classes. The next one is we have 4-layer of fully connected neural network. And then for that 13 class, we were able to accomplish 98% of accuracy. And then we were using different machine learning models, for example, features, TensorFlow, Keras, and sklearn.
So also on this diagram is basically the general representation of our work. We have collected the samples from the data. We basically send it to machine learning model, and afterwards we've got a prediction, and one of the outputs of the prediction you may see on the right part of the slide is basically we get probabilities of the detected objects. Thank you. So now coming to the lessons which we learned during this project. Basically, the software in this case is not a problem at all. Means building model, even just usual shallow neural network does a really good job. The data should be just balanced, and no special treatment of data should be done, because this is our data. We collect it, we decide which format and so on. But the challenge is coming from hardware side, which was expected a little, but was not expected so many challenges. So first of all, so this is the sensor itself. It was quite important to understand how it is working, what is the physics behind. And I will not come to this point right now because it's a lot. I may discuss about this long time and so on. But the first challenge is like this: all sensors must be preheated at least 24 hours in advance, and if it is new, even 72 hours. And on the bottom plot, you may see the time, which is basically integrated time of the sensor, and the scale is like the last point is 140 hours. And only at this point of like 140 hours of operation of a sensor, the data might be considered as a more or less stable and reliable, not before. Also, every time you turn it off, you should preheat it 24 hours. Surprise. Afterwards, the sensors are not identical to each other. This we did not expect as well. On the right side, on the right two plots, you may see the basically raw readings, raw data from the two sensors, which are placed at the same glass with the same object. At the same time, I collected, there is like microsecond to microsecond data synchronized, and the readings are completely different. Also, the readings are heavily dependent on the environment. Means if temperature changes of environment or humidity, then the readings are also change. And that's why actually we added the temperature and humidity sensor additionally to this gas sensor. It helped us to improve the data a little. Also, the acquisition cannot be done instantly. So at least, according to our experience, at least like 5 to 7 minutes, the measurements, so the sensor should be located in a constant environment. So it means that's why we use here the paper cover, so that no air flows inside, no temperature changes inside, and only afterwards data might be considered reliable. And now the interesting part, like how we deploy the model. So basically it is working, and for like nice representation of it, we decided to use also a Streamlit package, which simply creates a nice web interface for which is user-friendly. And now we are coming to live demo, and we are going to show simplified model. Due to all of these reasons, which I mentioned before, we have model only with 3 classes, just because it is working. I mean, it is working in different conditions and reliable.
So just to mention about the PowerPoint from Igor's last slide, we actually bought two identical sensor, but two sensor from the same company. And then it turns out that we measured the same thing and then we could have completely different result, which is totally got us in surprise. Yeah, so it's very sensitive pieces. And then there could be some little changes inside of each sensor. So.
Okay, well, now coming to the live demo. Right in this glass, I have coffee right now, and the sensor is already placed starting from the beginning of the presentation. And the sensor is connected to Arduino, as you may see here, and also on the bottom there is a temperature sensor, which is basically connected. Yeah. Now Hazel, press please reading data. And it is working. You may see the LED is blinking, and means the data is acquired. Yeah, well, let's see. Yeah, and prediction, it is coffee.
So just to tell you guys that we're not cheating, as coffee powder inside a cup. So.
So we may have some beer, which stays. Yeah. Beer. It may detect beer, and I hope it will be faster this beer because it is beer. This sensor also likes beer.
And then when it's testing, I'm gonna explain a little bit on the chart. So the one on the left-hand side is the probability. And then for simplification, that's why we only have 3 classes for today's demo, because we have those 3 samples sitting in front of us. And then on the left-hand side is the probability, which shows which one is the winner for the smell. And then on the right-hand side is the chart of those 6 elements that we mentioned earlier. So the x-axis is the time from about 10 seconds. And then the vertical, the y-axis is the value, the index of those 6 elements on the right-hand side that you see. And then
well, right now I have placed the sensor inside, and as I told you, according to our experiments, it should be inside at least 5 minutes. But let's try, and you will see that slowly it will be like if we so I don't know how much time that passed, like 1 or 2 minutes. Let's collect this data and try to predict, and you will see that it might be not correct at the beginning, which is predicted by us. Let's have a look. It is beer. Okay, I tell you, it likes beer.
Wow, this is unexpected because normally, usually live demo is not working perfectly. And then second is because it takes like 5 minutes for it to, the sensor picking up the smell from it.
No. No. I think it's enough. It's fine.
Okay.
Then we have one more sample.
So we prepare 3 samples, coffee, beer, and orange. So we're gonna try the last one to see if it works or not.
Orange. This looks like orange. And
zoom it.
Yes, still okay.
So let me just, when Igor is setting up, so I just mentioned about our website or web apps on Steamlit. So on the left-hand side is the picture of Igor and me taking with our sensor yesterday. And then top right-hand corner is my son helping me to take the sample of the food. We were like crazy taking samples from day to midday to night on different classes, and then going outside at 2 degrees and then chilling and then shuffling and then taking the samples. And then in the middle picture, it shows we try to cover the food so that the smell of the air is not like in the room and then mislead the category. And then the last picture was just showing some food that we decided to take, like coffee, breads, and wine, stuff like that. Okay, shall we try?
Yeah.
Okay.
Let's give it a try.
So this, we have orange in a cup, and then we just put it maybe a minute ago, and then let's see if it works.
But it might need up to 5 minutes.
What?
Better than expected.
Yeah. Wow. Surprise. Yeah. So, well, thank you very much. And
yeah, we would like to say many thanks to all team of Data Science Retreat, to all teachers who explained us a lot, nice topics, and answered to all of our questions, sometimes too nerdy questions. Many thanks to Jose, to Paul, our mentor, to Tristan, to all of the teams, all of you guys. We are really appreciated this time, and it was a really nice team. Thank you. Destroyed.
Okay, so questions from the chat. We can read them out loud or from the room about this project. Jeremy.
I have a question. Okay, so I'm coming here. I have a question regarding, so do you know how sensitive your sensor is? They are very busy with moving. Do you know how sensitive your sensor is? And I think it's related to another question which has been asked in the chat. How good does it perform when with detecting deliberately mixed odors? Like if you mix coffee and orange, like, I mean, if you want, like, can you use your sensor in a room, like instead of putting it in a sealed glass?
Well, first question was about the sensitivity. I mean, like, can it distinguish between different kinds of coffee? So we did not try this approach yet, identifying like different sorts of coffee or different sorts of beer. But what I may tell you for sure that if it is trained on one beer, then it for all other kinds of beer, it will identify that it is beer. And also coffee, for any different coffee, it is coffee. Answering to the second question, that was about mixing objects, and is it possible to measure in a room? Yes, it is possible, but some certain conditions should be met. Yeah, currently there are some limitations on this sensor, and this coming from the structure of the sensor body. And there should be a special case with a fan inside in order to correctly collect data, and yeah, then it might be used. But more developments are needed for this.
About the boundary conditions and so on. So 1 minute inside a container that is covered is what it takes to get a reading right now.
Well, currently, in order to be sure that it is working for demo, we decided to go to by the safe path, and what we've learned that in order to get reliable data stable, then the sensor first of all should be placed inside at least 5 minutes, and afterwards the data will be stabilized. Otherwise, you may have seen on some of the plots there are some jumps in values, and it is also related to some flying molecule inside. So it's still molecular. It's not this radio emission, or like it's not light. It's not sound. It still takes time to fly around. Quite slow process.
But it's kind of very inspiring that something like, you know, chemistry that happens in your nose, it's kind of replicated in a sensor. Sometimes we give it, we don't even give it a second thought that machines can see, which is kind of super interesting and spectacular. But a smell sounds like this ignore sense.
Yeah. So at the beginning, I said the sky is the limit because there's tons of potential use case for this product. I could like spend another 5 hours just telling you guys this user case. So you guys also like this can also be specialized in particularly on wine. Like there's all kinds of different wine in the world, like white wine, red wine, and all that champagne and stuff like that. So it could very specialize on one category and then do it really deep in-depth machine learning as well.
Right. So there's a question on the chat. Where did you buy the sensor?
Well,
black market in Russia.
No. Actually, we were surprised, and we wanted to buy it online, but afterwards realized that it is real shop in Berlin. That's you may buy all of these toys for hardware nerds.
It's actually also a tiny ML project, tiny ML. So there's all kinds of application on that terminal itself. It could detect the light, the temperature of the room, the everything. Like you can even play rock, paper, scissors with the terminal. Anyway.
And how many categories could you potentially have after your experience here? So if you go to a supermarket and scan the hell out of everything there.
So I think it is not a big deal for at least 50 categories. So it is 5. Yeah, there should be considered some conditions under the samples collected, and then the number of categories is not a big deal. It's even shallow networks do really well job for this.
So for applications, I can imagine using a sensor. If it's only €30, you can put that in a container that is carrying fruit that it's going bad. And sometimes you are shipping fruit all over the world. The fruit is bad when you only realize when you arrive and open the box.
Actually, have you guys have experience? You buy a bag of mandarin, the small orange, and then it turns out that one of them is rotten. It could also do that, or on a big truck of tomato, and then like there's 500 tomato, and then one of them is rotten. This thing also can detect that.
So the smell of rotten fruit is actually very noticeable. So it's easy to detect. Oh, that's very useful, actually. Okay, cool. So thank you, guys. Good project. Okay, so we're experiencing something exciting, live demos working. All right. So for our next presentation, we're going to deal with a problem that I have. So I go to classes for dancing and I don't remember much. And I think this is a pretty common problem. Everybody has experienced it. What we used to do before mobile phone video, we kind of drew stick figures to remember the steps and drew kind of a little comic of the steps. And now we record a video. We think that with that, we will remember things, but we never watch the video again, or if we do, it doesn't really help with memory. So this team decided to do something about it. So can you actually find labels automatically from just watching video of people dancing? And then those labels are meaningful to a human, so you can remember that. And this is what the sales annotation team will do. So here is Anna and Eero.
Thank you. Thank you for joining us here today. We are having a project where we are trying to create salsa annotation using machine learning. And as you probably already figured out, I'm Eero, and this is Anna. And learning to dance is really hard. And I have myself so many dance videos and so many notebooks filled with stuff. And when I'm now looking at the dance videos, it's really hard to kind of see what happened because people are turning around and it's just really hard to kind of observe. And especially for beginning dancers, they don't have the skill to describe what they are seeing. They don't have the skill to observe what's going on. And when you can't that, you can't remember, you can't learn. And that's the step we are trying to come over. And there are some annotation tools, or at least there was. But these either require that somebody does the annotation for hand. It's either a teacher who puts it in, or you have to do it yourself. But if you're a beginner dancer, you're not going to be able to do that. So therefore, we wanted to use machine learning to solve it. And we have therefore created the Salsa annotator as a machine learning option. And what we are trying to do is to start with the simple Salsa video, a handheld mobile phone camera. I mean, this has been solved earlier with complicated studio setup with many cameras and movement sensors, but we want to have something that people going to workshops can use. So therefore, we have a
1, 2, 3, 4, basic 6, 7, and 1, 2, 3, 5, 6, 7, 1, 2, 3, single right turn, go. 1, 2.
Yeah. So we are doing a model that has two different stages. First, we do post detection, and then we predict labels later out of this. And the post detection is really one of the keys here, because the video, they are big, there's lots of data. And with the post detection, we are cutting down on the amount of data we need to analyze and use for predictions, and also we are using open post because it's a very lightweight model. It's something that potentially could be used just in a handheld device too. And also the post detection helps to focus the analysis on the movement and the people. And there are some serious problems with the salsa because there are so many different salsa styles. People dance on 1, they dance on 2, they dance Cuban. There is no single annotation system either. So it's not like in ballet or some other where you have a very formalized system that you can use. And there are different artistic expressions. So people dance the same thing in very different ways. You might be a professional show dancer, adding lots of flow and cool stuff, or you are a beginner who is just trying to like get through the thing. And in dancing, you have also people are rotating all the time, and you somehow need to like allow the system to learn that these things are happening in different positions. And we tried to use YouTube, but that did really not work for us because there wasn't enough YouTube videos with single dancers doing the same things. There were all of kinds of things happening, but we need many examples of the same thing happening for the computer to be able to learn. And it was very time consuming to try to label all these different things and end up with so many different classes that we can't use. So therefore, what we did is that we created a choreography and a crowd campaign. And we made a video and so simple choreography that people actually are able to do it. You don't need a professional dancer to go through it. And what we ask people to do is to do 2 basic steps, 2 right turns, 2 side basics, 2 Cuban basics, and 2 Suzuki's. It's easy enough. Any salsa dancer can do that without much practice. And people started to send us videos. So we are getting videos in still. So we have kind of a data pipeline where we do start from the videos, which we resize a little bit. We take them to open posts. Now we are using Collab, but that could be done in a different way. And out of that, we get the skeleton videos you have already seen. And from open post, we get 2D coordinates. Unfortunately, we can't get like coordinates for the real space. So there are coordinates in the picture, which is sometimes misleading. And we, of course, then do some imputation of missing values, the stick figures, the poses, there's some jitter, there's some random movement that's coming from the pose estimation because it's a lightweight model. So we are smoothing that out. And then we normalize for each person so that we are only looking at the space they are actually using in while they're dancing, so that we are cutting away. It's kind of like a bounded box for the dancing. And then we are augmenting the data a little bit, adding different perspectives and stuff like that, so that we get more data out of it. And then we still need to do manual labeling where we mark where the different figures start, even if people are using a choreography. But that's something that, yeah. And in the end, we have then 384 examples of each figure, and roughly 100 frames per figure.
Okay, so when we have our video processes and then we get the coordinates out of this open pose program, we move to the second part of our model to predict the name of the figures. So unfortunately for this kind of task, we didn't find any pre-trained network that we could use. So this action classification problem is a little bit different, of course, from the image classification. There are already some studies that have generated some data for action, but actually the data that they use is very different. It's, for instance, being able to distinguish throwing a ball from drinking water. So I think this kind of architecture wouldn't work for our problem, in which the difference between different steps are very subtle, as you will see later. So we build the model from scratch. So our input right now in this part are the coordinates that we got from OpenPose, and then the model that we build using TensorFlow Keras has 3 layers. The first layer is a layer from gate recurrent units, followed by 2 fully connected layers. Why this architecture? Because of course we want to keep the temporal aspect that our data has. So we have a consecutive an ordered set of coordinates that is moving in a coherent way in time. So the output layer has 5 nodes. With the 5 classes, we are able to distinguish. Sorry if this kind of label maybe is not very intuitive for somebody who doesn't know. Basically, I don't know if you can see my feet in the video, probably not, but for the one being here, we would like the computer to distinguish between doing this, for instance, which is a side step, and doing this, which is a Cuban bicycle step. So there are many possible figures for a start, and then prove that this kind of approach can work. We decide to start with only 5 classes for our problem. So basically the model we predict the probability of getting one of these figures, and then the one with highest probability will be the label for our problem. So we tried different architectures that have similarities to the one that I presented here. We could play a little bit around with adding more recurrent layers, changing the size of the recurrent units, also changing the size a little bit of the connected layer, but actually the accuracy of the prediction didn't change too much. So here I will show an example. In the left side, you can see training and validation losses. So we can see that from the orange curve, after 20 epochs, we can stop our training and then take the model that we have at that point, because after that we see overtraining. And then on the right side, you can see the accuracy for both the validation and the training set. So we reach an accuracy of around 60%, which is 3 times higher than the one that you would expect from a random generation that will be 20% in our case, in which we have 5 classes. So here you can see, for instance, 2 examples in the validation set of how, what our model predicts. In the left side, you have a right predicted label, in which you can see that, I cannot see, sorry. You have 80% of the figure that is being executed to be a basic step, and it is. And in the right side, you see an example in which is completely misclassified the basic from the Cuban basic. Here now, I'm presenting a general summary of the results that we get in the whole validation set. So we can see that more or less all the metrics show a similar prediction for the 5 figures, which is also expected because we make sure that the data that we are working with is a balanced data set. For this reason, we created a choreography with the same amount of elements. On the right, you can see the confusion matrix in which you can see how many times a figure is misclassified by another figure. So let's say if you go on the top row and then you move to the right, you can see that a basic step is 19 times correct, predicted correctly, 1 time is misclassified with the right turn, and so on. So I think these numbers doesn't tell too much. So I think it's better to see how the prediction looks in a video. So our idea of the project, of course, is to end up with the application in which a person can upload a video, and then we run our model prediction, and we will get the names of the figures that the person is doing. So let's see. This is still not finished, so it's just a prototype of how it would look like. Okay, so one thing, remember that our pipeline has 2 steps. The first one is to predict the skeletons over which actually the labeling is predicting, because getting the skeletons requires the use of GPU, and we run this in Colab. We cannot present still this the whole flow automatically. So what we did, we select 3 videos that were not used neither in the training or in the validation set, and then we run open pause on that. We have the data. We also indicate where every figure starts. This is something that unfortunately the program cannot do still, but we have some ideas on how this could be done. And what is running here in real time is just the labeling. So the calculation of the label for the size of video we are using is quite fast. So let's see how it looks. We go here, we take 1 video, then it's uploading. And then you have in the first columns, the predictions, in the right column, the true labels. This is only for demonstration because, of course, in the application, you will not know which the labels are. This is just to show if the program is working or not. Yeah, here is 100% accuracy. Actually, all the steps that this person is doing are reproduced exactly with 100% of accuracy. Of course, when I see this girl dancing, I can figure out why the program can recognize very well what she's doing. If you take a look, she's really doing the steps properly. There is not too much movement of the arms, something that actually when you are dancing salsa is not the case. She's doing like this just because she was repeating the choreography that we sent, in which I think for the purpose of this exercise, we really did with not too much movement. So if we check now a video, another one, let's see what happened. So here we have Basil. It's a longer choreography, so we have more labels. And then you can start seeing that there are steps that are correct, are predicted in a proper way, but there are some that are misclassified. For instance, the first step, you have that a basic step was misclassified with a Cuban basic, but let's see what Basil is doing. It's not that he's dancing wrong, all the contrary, but he has much more fluidity in the arms than the previous dancer. Also, we realized that the basic still is not actually that you do all the time the basic in line. You could also cross your feet a little bit. And of course, we are not pretending with this type of application to say that people is dancing wrong. No, this is not the, the idea. This is one of the things that we realize with this kind of apps, that saying that something is wrong or right is not really accurate, because dance is very open, so you can do whatever thing you want. But what is sure is that for this type of problem, we need much more data, because then we can actually capture all these little difference in styles that people can have while they are dancing. But still, we think that having this kind of application for somebody that can just take their phone and then take a video, then record it, and then find what they are doing, right? So let's continue then, and let's just move to a future work that we think that can really improve what we have until now. So we have two directions in which we would like to work. The first one is how to improve the accuracy of the model that we already have without changing too much. So first of all, as I already said, and as you all know, more data. This is fine because we have still this link open. We are collecting more videos. There are even people in this room who owe me some videos that please, we can collect it still even if the demo date is finished. We can do other things. We have a very nice suggestion from Tristan that we are really happy to try. We're really happy to try, sorry. That is try to use self-supervised learning for our problem. And what does it mean? With the data that we already had, we can try to take our network architecture and then to solve a slightly different problem. So we will remove the last layer of our classifier, and then instead we will have an auto-regression problem. So we will try from the frames that we have to predict which is the next one. So for that, we don't need any layer. So with this kind of model, maybe the network learns a little bit better about the movement itself. Then we can come back again to our classifier, remove again this last layer and add our classifier layer, and then to do some fine tuning in this network. There is another way to go that I was really, we were very surprised to see that something like this can happen. Apparently, in machine learning, at the end, everything can be reduced to image and also motion. So we were surprised to see some, unfortunately, I don't have here the examples, but there are some papers that suggest to transform your skeleton collection of frames into just an RGB image. And then, of course, once you have an RGB image, you can use all the pre-trained neural network that exists in computer vision, and maybe the prediction is better, and then we don't have to start the learning from scratch.
And another way we are hoping to go is to extend the functionality a little bit so that we can easily from the open post coordinates calculate things like how much people are moving their shoulders and how soft they are dancing and things like that. And also when we are looking at the wrongly labeled figures, it looks like that it might be better to use only the count to 4 instead of 8. So to use smaller units to label, kind of half the size, the figure length that we are doing now, because many of these figures have the same element in the beginning or end, which then confuses the learning. And the obvious thing is we need to add beat detection. And there are already models who do beat detection. We just need to kind of put it in and make sure that it's working together with our data. And then we need to extend this to a couple, which I think is possible. It might be that we have to drop open posts, but there are some other post detection systems that are better, but they are harder to process. They are much heavier. So it's kind of becomes a choice then. Is it possible to gonna do fast in an app, or are we gonna have a heavy processing in the backbone of it somewhere hidden. And of course, now we did the choreography with 5 labels because this is easy. This is something that people can easily learn. So we have to make more choreography so that we get more examples of other figures, so that we in the end then have like 10, 15, 20, 25, and hopefully we have then enough names of figures that it actually becomes interesting, because with just these 5, it's a proof of concept. It's not something that you can actually really use yet. And we would like to thank our mentors, Tristan and Marcos, all the dancers who were making videos for us, the data science retreat team, all the teachers, and of course, all the participants who have been on this journey together with us. Thank you.
Awesome. So you two are dancers, right? So you're Cuban, so I don't have to ask you. So, and you are a tango dancer, but also salsa dancer, right? So this is what I keep saying, like you can solve your problems with machine learning. So any problem that you have, you can try to solve it. Okay. So questions from the audience, questions from online, anything that you want to know about how to train models to teach you how to dance better? Because I'm sure they have found roadblocks that they are interested in their own right. So I have some questions, but I would like to hear yours first.
So if you have a model that's good enough for salsa, do you think you can just retrain it to do similar thing for tango, for example?
I hope so. That's something, tango is a little bit happening more inside, so it probably would require more precision and even more data to it to be working. But I think that the way to go forward this project is really to find teachers who are interested so that they can teach their students a choreography and have several teachers teach the same choreography to the students. And that way it would be easy to get all the data we need. And if that works, I think you could teach any dance.
Yeah, I think that right now we present a model that works for one couple. I think that if we manage to make it work for a couple dancing in salsa, then it will be probably extended to tango. Because the main problem that we have now is how this, for instance, the detection works very well when you have one person. One of the problems that we saw with open pose in a dancer, especially when you are dancing very close, is that some parts of the body of your partner can be associated to body of you. But this is also related to the way open pose works, that doesn't do object detection. So it's just identify key parts of the body, and then from there it constructs the whole body. In this sense, maybe another pose detection program that do actually person detection first is better. But yeah, I mean, if we manage to do to have this program working for a couple in salsa, I think it wouldn't be a problem to extend it to tango. With tango. Yeah. Yeah, it works. It works fine. Yeah. This type of couple, yes, but I mean, it depends of the scenario, because for instance, one of the problems that most of the videos of dancing class have mirrors. Then, for instance, in open pose, either you detect one person or you detect all the things that the program thinks that are persons in this frame. And sometimes then you have your shadow being another person, of course, the reflection in the mirror being another, sometimes even a lamp. So then it has a lot of pre-processing because you don't know actually what you will expect when you run open pose. This was actually a very good one, that they are dancing in a roof, and then there is not too many things around, and then sometimes the additional skeleton that you see is because of the shadows, because there is sand.
For that one that works, you can get know because you don't have the labels, right? So how far are you guys from having labels so that somebody could bring you a video and you give them the same way that you give them the stick figures now, you give them the labels?
But you mean for a single person dancing or for a couple? Yeah, it's a hard question because, I mean, when we start this project and we had this idea like, yeah, it will be nice to have, of course, we wanted to label a couple dancing. But then, I mean, it turns out that, for instance, Aero dance LA salsa and more Cuban salsa. And then we start realizing how different the type of salsas are, even for the annotation. So, I mean, here we include a figure that actually is from LA. I didn't know that this exists before, this Susie Q. So, it's yeah, we should think. I mean, it's more than about what do you really want to do with the app. One of the things, like maybe it sounds a little bit more theoretical, but we were thinking that it will be possible. Like you can, of course, not add all the lace boats that you could, because I mean, there are many, many names. And somebody, I mean, whatever person is free to name a figure as they want. What it could be maybe good to have is like as many categories that you can see that can be representing most of the movement that you know. And then if you have a model that can make good feature extraction from the video, that then you can take other figures and then see to which figure is more similar. And then maybe you could cluster. I mean, but I don't know if this is interesting for somebody who is dancing, to see that a figure is similar to another one, that they belong to the same families. I don't know.
The funny thing is that in my experience, the teachers also don't have names for these things. Maybe 20% of the things have a name, the rest don't. So it's very hard for them to I don't know how they do it. And just for people who are not dancers, right? It takes about an hour of class time to learn something that is 15 seconds, 13 seconds, 30 seconds of performance. And then you forget. So I've been going to classes for 20 years, perhaps. And I remember some limited amount of moves. And then I get a new one, I forget another one. So it's not worth it. So this is a big thing, right? So when we all figure out that this could be a project, we all smile to each other like, and I think everybody who's a dancer and is watching this is going to be that smile like, really, you can do this? So I really hope that you can continue pushing it through and you get to a point where people can benefit from this, because it will be really useful. If you would make humanity dance better or remember dance moves better, which is a big thing.
I mean, we cannot imagine all the potential that this could have, but then when you speak with a teacher, they actually can tell you what is the more important, because they have been teaching, they know what the students have more problems, so it's probably the good. We had actually help of a teacher for the choreography who said, okay, if you did these 5 steps, everybody can do that. Because at the beginning, we were also not very clear which steps, including the choreo.
I think that the biggest challenge for getting further is to have enough videos with choreographies. And I really think that the choreography is the only way to do it. Nobody's going to be willing to pay the kind of money that it takes to label thousands of dance videos. But people can do choreographies and it's fun. And I know many teachers do teach choreographies, so it's doable. We just need maybe 1,000 examples of each figure, or but like the choreography we did, you repeated each figure 8 times during the choreography. So one video has 8 samples in it. So if you do the same kind of approach, you need a couple of 100 videos and for each choreography, and it's working.
But then if you have series of this, just show up to Salsa School and record everybody who lets you. Right?
No, I think people need to do that.
People need to do that.
Yeah, I mean, it takes too much time to collect hundreds and hundreds of videos. Okay. So, and that's part of the reason why we are trying to do it such a light way, easy way that people can use any device to do it. So.
And then if you ask people to record themselves at home, you have the problem with mirrors, with backgrounds that are kind of not that smooth.
Yeah, that's the problem.
Cool. Okay, for whoever is watching online, this was the end. We have 5 projects this time, so thank you for your attention. And that was batch 28 of Data Science Retreat. So if you're watching this and you're looking for data scientists and you have a company that could do better with more talent in this area, by all means, check their profiles. We will tweet, we will post on LinkedIn the videos after they're processed and so on. So you will find that it's not hard to find these people, right? So by all means, try to contact them if you are hiring data scientists. Okay, thank you so much for your attention.